here, M0NTV, and welcome back to my shack and to another homebrew video. And finally, to the mixers. But first, a joke. A vicar, one Sunday morning, preaches an exceptionally long and tedious sermon. And at the end of the service, the congregation just file out of church. Nobody says anything. Nobody even looks at him, apart from one bloke. And this one bloke goes straight up to him and he says, "Do you know what, Rev?" He says, "Your sermon today reminded me of the peace and the love of God." Well, the vicar couldn't believe it. He said, "Really? Really?" He said, "Nobody's ever said anything about my sermons like that before." He says, "But I got to know." He says, "What was it about my sermon that reminded you of the peace and the love of God?" And the guy looks at him and he says, "Well, Rev, it's like this. It reminded me of the peace of God because it passed all human understanding. And it reminded me of the love of God because it endured forever." I'm here all week. But I don't want to do either of those two things with this huge and potentially quite confusing topic of mixers. So I'm going to break this material down into a number of videos. So 3 things before we get started. Firstly, those of you that have followed my channel for a while will think, hang on a minute, haven't you already done a trilogy of videos on homebrewing a diode ring double balance mixer? Yes, I have. And I'm certainly not going to rehash all that material because I've been back and watched them and in my humble opinion, that's still good information. So what I want to do this time is actually present some supplementary material. So to tackle some of the things that I didn't tackle last time, or if I've done something differently this time, you know, with experience, to do that. So hopefully the 2 sets of videos will mesh together and without too much repetition. So what I would suggest is if you're interested in this stuff, after this video, you might want to go back and check out that video series I did. I think it was January 2022. Yeah. Not this January before, but you'll find it all there. So that's the first thing. So I'm going to be hopefully presenting some different material to the stuff I did last time and not just repeating. Secondly will be the focus, because last time I was focusing exclusively on, well, if you imagine a kind of superhet design, on receive, what would be the first mixer? The one that converts your RF signal coming in down to the IF frequency. Or on transmit will be the second mixer, the one that takes your modulated signal at the IF and mixes it up or down to your transmit frequency. That's what I concentrated on. I didn't give a lot of attention at all to the second mixer on receive, the first mixer on transmit, which is usually known as on receive as the product detector and on transmit as the balanced modulator. So that's what we're going to concentrate on. We're going to concentrate on building a product detector / balanced modulator. It's going to do double duty. And thirdly, I'm going to start at the end. Which I know sounds a bit weird. But what I mean is, instead of starting right at the beginning and showing you how I build it all and all that kind of stuff, we're going to do the testing today, right? So I've already been doing some building, as you can probably imagine. And I've got a whole bunch of different mixers. And I'll show you those in a minute. But I want to show you, so you can see for yourself, the difference that some little tweaks and additions can make to the mixer. So once we've worked out what works and what's good, then we can worry about how we build it, and I'll get to that in a future video. So first we're just going to have a look at some different kind of variations of that basic double balanced diode ring mixer and see how they perform. I hope this is of some interest to you. If so, stay tuned. Now, there's different ways you can test mixers, and in the last trilogy that I did a whole video on testing times for mixers, I think I called it, and I showed you some different things you can use depending on what equipment you've got. For our purposes today, I'm not going to do all that stuff again, and really I'm not so much interested right now in showing you how you can test a mixer as much as showing you the difference that different mixer designs make. So for the sake of simplicity and clarity, I'm going to use exclusively my Siglent Spectrum Analyzer, and I'm going to show you in a moment some of the tests I've done, and you can see for yourself. But before that, I'm going to show you the mixers that we're actually going to be testing.
Well, we're going to start with just the classic vanilla diode ring double balanced mixer. So here's one I prepared earlier, and you'll see this is about as simple as it gets. So you can see there the two trifilar wound transformers, which are in essence balance, really, which are taking the balanced signal of the diode ring in the middle there, you can see, to the unbalanced outputs here with just a signal and a ground. And you can see the diode ring, those four Schottky signal diodes in the middle there. 1N5711s, I believe. And so that's the first one, and you'll see that it is that. There's nothing else. There's no diplexers, there's no any form of impedance matching, there's no 100 ohm pots to balance out any inaccuracies in the windings. All of these are things that could go on. This is why I call it the vanilla one, really. And the truth is, this would work very well as a kind of bog standard mixer, and we'll see how it performs as a modulator in a bit. But so that's the first one we're going to start with. Now, the next one we're going to use, and I'm not going to go into any details at the minute of how I'm building this. This will all be for another video. This is the one which actually is going to go into this rig that I'm building. The one in the tin is just one I have in the drawer that I use just for testing purposes. But this is the one that I built, and you'll see it's similar in many ways, but it's got more stuff going on. So the local oscillator port is going here. So the trifilar windings are the same, diode rings the same, but over here, this is the W7EL Roy Llewellyn audio diplexer, which sits on the what's now the audio port, and which and after that diplexer, audio diplexer, that you go to this relay here, which splits then to the receive side, which is going to be on receive. That will go to the audio amplifier and the loudspeaker, and on the transmit side, when the signal will be coming in, that will go to the microphone amplifier and the microphone. And so that is like a souped up version of what I've just shown you, and we'll be testing that as well. Now, I had contact from Andy, G0POY, and Andy is a keen home brewer. And not only that, but he, in his professional life, he's an electronics engineer, so he really does know what he's talking about. And Andy has had printed up a whole bunch of these little boards for home brewing diode ring mixers. Let me just try and get in there a bit closer so you can see. And they really are quite wonderful. And actually, you'll see there, this is one he sent me, and he sent me a whole load of this stuff, and I've got to give a big shout out to him because it's so very kind. A whole board, not just the boards, but toroids and also the diodes. And if I get close up here, you can see these are dual diodes, surface mount diodes. So there's 2 on each one of those things. But he's designed the board so that actually you could solder in just, traditional through-hole diodes around the outside as well. So it's really, really clever. Now, I confess I'm sorry, Andy, I haven't actually made up any myself yet. This is one that he made up and sent me. I mean, how neat is that? Look at those toroids. I mean, that is just something else. Very, very well done. So, so now, so we're going to try out Andy's boards as well and see how that compares with mine. It's certainly a lot smaller and neater, and so that's good to know. And we're also going to put through its paces a commercial mixer, and I'm not going to say anything about it, but you can probably read what it is on the top there. And all right, so this is it's still available, and from lots of electronics firms. So this is a commercially made double balanced diode ring mixer, which I've just fitted into the same old case. And so just for the sake of comparison, we're going to use the professional one as well. And the last thing I'm going to show you won't make much sense to you now, but I'm going to show you anyway, which is another separate little board. Now, this is not a mixer, but this is going to be an add-on to a mixer. And what this is, ignore this coil here. This is an RF diplexer. So it's effectively 2 tuned circuits. It's a series and a parallel tuned circuit, tuned to 13.3 megahertz, my IF frequency. And again, number 2 of that last trilogy was called Diving Deeper into the Diplexer, where I go into exactly how I build this, so you can check that out. And we're going to try fitting this in as well to see what difference this makes. Now, the addition is this here. This is an impedance matching transformer, and I'll perhaps say a little bit more about that when we get to it. But that's something else that we're going to be putting in and seeing what difference it makes. Right, well, we better get on with it. So, the test conditions. You'll see here my signal generator. So, channel 1 is simulating the local oscillator, so that's the frequency of 13.3 megahertz, which is my IF frequency, and you'll see I'm running that at 1.4 volts peak to peak, which equates to 7 dBm, about 5 milliwatts, which is what you generally would tend to kind of feed a diode ring double balanced mixer with. And channel 2 down the bottom there is a 1 kilohertz sine wave, and that's running at just 200 millivolts peak to peak. So all the different mixers I've shown you, I'm going to be feeding them the same, exactly the same parameters. And then obviously things will change when I switch to the SI5351.
So here we go. Let's have a look at some of the results of my tests. So I applied, as I said, those frequencies I've just shown you to the mixer, and then from the, what would be the RF port, I connected into the input of my spectrum analyzer, and this is what I got. So, okay, so just to show you, if you've seen any of my videos before, you'll know, fortunately my spectrum analyzer has its own LAN built in, which means I can kind of just find a web page with it on, and even control it from the web page, which is really useful. So these are just some screen grabs of the tests that I did. So this first one you're seeing is my, all-purpose vanilla bog standard mixer fed with the signal generator. And so you'll see there in the center, there's the carrier, which is marker 1, and I've just got marker 2 on the lower sideband signal, which is incidentally the one that we'll be interested in because it's because we're inverting the signal to the lower sideband and then inverting it again through the next mixer to upper sideband. That's the one we'll be using. Now you'll see we got about 33 dBm of carrier suppression, which is not great. I'd want to see more than that. But what I would just say is that for a mixer, for a first mixer on receive, second mixer on transmit, this would probably be fine, because if you think about it, if those 3 frequencies that you are dealing with, your local oscillator, your RF and your IF frequencies, are all far enough apart, then you can filter out all the stuff that you don't need, and it's not so critical. Where it is critical is particularly in a modulator, and to be completely honest with you, most of the problems I've had with my homebrew rigs can be traced back to insufficient carrier suppression in the balanced modulator. And the thing is, if you don't fix this here, you're going to have a dickens of a job trying to filter out that carrier, without adversely affecting the quality of your audio signal. And that's the problem, is because when you're dealing with audio frequencies, I'm testing this with 1 kilohertz. So those sidebands are 1 kilohertz above and below of the carrier. So you haven't got a lot of room to maneuver, much less filter. So really you do need to get that carrier down as low as you possibly can. And when those signals are all spread much further apart, it's not so much a problem, but it is a problem with the modulators, which is why I'm doing this video. So that's the basic setup. So could do better, I think, is the moral of this tale. But you might look at that and think, well, it's because you ain't built it very well. If you build it better, then it'll look better, possibly. But that's why I want you to see some of the other ones. So next up will be Andy, G0POY, his mixer. Okay, so this is mine, this is Andy's. Spot the difference. Okay, let me go back. This is mine, this is Andy's. Other than the fact that the noise floor is slightly higher, they're practically identical, which actually gave me great hope, because I thought, well, Andy knows what he's doing, and he's produced this board, and it's well made, and you can see that his results are virtually identical to mine. So I thought, well, that's good. It's not just that I've not built it very well, and in actual fact, I think you'll find if you compare my effort and Andy's efforts with what I'm about to show you, you'll see actually we're punching above our weight, really, because the next one I'm going to show you is the commercial mixer, right? Exactly the same test conditions, and this is what the commercial mixer looks like. Look at that! That's not even 25 dB of carrier suppression. So essentially, both mine and Andy's mixers beat that commercial one, hands down, right? As a modulator. And there's, bear in mind, again, I'm pressing these mixers into service as a modulator, and you could argue, well, they weren't intended to be modulators; they're intended to be general purpose mixers, and that, that's fair enough. But I want mine to do double duty. I want mine to be a product detector and to be a modulator, and I want, as far as possible, to keep the design consistent throughout all the mixers, if possible. So now. Also, your mileage may vary depending on how you drive these. You could drive them harder or softer, whatever, and you may get different results. But I thought it's very interesting to see that actually that basic mixer design used as a modulator does not, as far as my testing goes, and I'm not an expert, but as far as my tests go, does not produce the best results on its own. It's fine for a standard mixer, but not great for a modulator. So, what can we do about it? If it's a problem across not just my mixers, but other mixers, what can we do? Well, what we can do is we can do something about the impedance match on the IF port, which in the case of our modulator is the audio port. And this is this W7EL Roy Llewellyn audio diplexer, which acts a bit as a filter, but also crucially lets that audio port see a good 50 ohms termination. And if you do that and you put the Roy Llewellyn diplexer on, you get, look at that. Look at that. I don't often say this, but folks, I don't think it gets much better than that. I mean, there is no carrier, there are no close-in harmonics, and you've got, I think that's 59 dB of carrier suppression. Absolutely superb, right? And you think, well, my goodness, for a few extra components, of course you're going to do that. Why wouldn't you? So it's looking good, the same basic design, a few other components on the audio port, and the job's a good one. Except when you think, well, hang on a minute, because at the moment, one mixer port is going to the 50 ohms termination of the spectrum analyzer. The other two are being fed by my 50 ohm output impedance signal generator. What happens when you disconnect the signal generator and connect in your SI5351? Now, actually, in truth, I'm not completely disconnecting the signal generator because I'm still using the 1 kilohertz sine wave from it, but the local oscillator I'm swapping out. So now, instead of using the signal generator, I'm going to use the SI5351. You get this. Oh dear. The wheels have fallen off once again. We're back to pretty rubbish carrier suppression, and also we've got some, close-in harmonics as well. And you think, oh dear, well, maybe you're driving it too hard or whatever. And you can adjust the drive of the SI5351. You can do it in software. You can set it to 2, 4, 6 or 8 milliamps. Or you can do it in hardware via, you could amplify it if needs be, or you can attenuate it. But you look at that and you think, well, that's dreadful. But we've got our magic Roy Llewellyn diplexer. We'll just stick that on it, and it all will be well. So let's do that. So that's what I did. So I took my mixer, fed by the SI5351, but I stuck the Roy Llewellyn diplexer on it, and I got what? I mean, just a minute. I had that. I stuck the W7EL audio diplexer on it, and I got that. I mean, there's no difference apart from taking out those close-in harmonics. It's done virtually nothing to attenuate that carrier. And I had to stop and walk away and think about this for a while, which is not a bad thing to do. So I kind of thought, well, hang on a minute. How can we have a situation where I had the audio diplexer, which had such dramatic effect when I used the SIG-Gen, and yet for the SI5351, it didn't make any difference at all? Which boils down to this question. What's the difference then, considering everything else is the same, what's the difference between the signal from my signal generator and the signal from my SI5351? And it seemed to me there were potentially three differences. One was the drive levels that I've mentioned. The second was the fact that my signal generator was feeding a sine wave. And there is, how can I put this? A conversation, full-blown argument, whatever you, I don't know, depends where you stand really, about what you should feed a diode ring mixer. Technically, I see the value of feeding it a square wave, because clearly those, if you think in the time domain of a square wave, that a sine wave gradually ramps up and goes down, where a square wave is on and then it's off, and so it energizes the diodes more quickly. So it turns the diodes on more quickly. So the mixing should be more efficient. However, the truth is, well, what makes a square wave a square wave? A whole truckload of harmonics, right? And do you really want to be feeding all those harmonics into your modulator when you're concerned about the close-in harmonics that you've already got, and you're messing around with 1 kilohertz tones, you could have an awful lot of intermodulation stuff going in there that you don't really want to deal with. So I'm a bit on the fence about that, really. But anyway, be that as it may, the SI5351 puts out a square wave-ish. It's not a perfect square wave, but it's certainly not a sine wave. So I thought, well, maybe that's an issue. Maybe that needs cleaning up, right? Clean up, low-pass filter it effectively and get rid of some of those harmonics. But the third thing was, it suddenly occurred to me, I wonder what the output impedance of the SI5351 is. Because the port is wanting 50 ohms. I bet it's not 50 ohms. So I did some impedance tests, and I haven't got time to go into this now, and this is almost certainly a useful topic for another video about how do you test output impedance. But anyway, I did some output testing, and I calculated my rough and ready measurements were that I'd got something like a 93 ohm output impedance from my SI5351 powered VFO. And when I looked in the data sheet of the SI5351, that credits it as, I think, 85 ohms. So I got 92, 93. It says 85. So I thought, well, I'm in the right kind of ballpark figure. But it's not 50 ohms, is it? So, that's really like a 2-to-1 SWR. So you are going to get a fair bit of reflected signal there. So I kind of thought, okay, what do I need? I probably need a little bit of attenuation. I need possibly some low-pass filtering. But most importantly, I need that port to see 50 ohms. What can I build that will give me some attenuation, some filtering, and a good 50 ohms termination? A diplexer is the answer to that question. And please go and watch the second video of my last trilogy, diving deeper into the diplexer, where I will detail there exactly how I built that diplexer. And the one I showed you a few minutes ago is built to that exact design. Only this time, instead of it going on the IF port, this diplexer is going to go on the local oscillator, which I've never tried before. And also, the only thing that's different from that diplexer video was I put as well a little impedance matching transformer on. So I calculated, taking 92 ohms down to 50 ohms. So it works out, I think I'd got 13 turns on the primary, which is the 92 ohms side, and 10 turns on the secondary, which is the 50 ohms side, and that gave me the right impedance transformation ratio. And so I put that on there as well, you know, kind of belt and braces really. And so I thought, okay, well, we'll do that and see what it looks like. Well, this is what it looked like when I added that to it. So when I took the basic mixer plus the audio diplexer and I added to that on the local oscillator that RF diplexer, this is what I ended up with. Wow. And order is restored to the universe. And just to show you how good this is, I don't know whether you noticed, but when I was doing these same tests with the signal generator, the noise floor was sitting about minus 80 dBm. So the noise floor has dropped almost 20 dB. So actually, these results are even better, even though you can see a bit of carrier there, and you couldn't see anything before. That's because the noise floor was 20 dB higher. Actually, we've got here 66 dB of carrier suppression. That is outstanding. That means that that carrier there, which is a marker 1, is that signal is more than 4 million times weaker than that lower sideband signal, which is marker 2. So that will do nicely. So when it does come to building, we're going to use one of these. So that's the my basic mixer plus the W7EL audio diplexer, and we're going to use one of these, which is my RF diplexer with the impedance matching transformer on the local oscillator port. And with these two together, I should get a nice clean signal from a modulator, which will be great then going forward through the IF section. When it comes to the other mixer, I might just try and get away with the vanilla version, but you know, if I get worried about it, I'll just build another diplexer and stick that on the IF port probably. But we'll worry about that when we get to it. Now, that's enough for today. The next video, we're going to dig in to some of the stuff involved in building this, but some of the stuff that I've not tackled before, and specifically next time, I want to tackle the diodes in the diode ring and how you match those 4 diodes so that your diode ring is the most efficient. And there's different ways you can do this, but I've been playing around with a cool little design that I think will help a lot of people. I'm hoping it will, and so that's what I'm going to concentrate on next time. We're going to think about matching our diodes, and so we can build a really good diode ring, and put that with the transformers and a few more components for your audio diplexer, and that's the modulator product detector built. And as I said, I've already covered the diplexer pretty well, but I will just talk about that impedance matching transformer that I put on there as well. So that's for next time. I've got a bit of holiday coming up, so you might not see me for a few weeks. But in the meantime, thank you ever so much for watching. Keep those irons hot, and I'll see you on the next video. Thanks very much. Bye-bye. 73.